So this video will cover section 19.4. This is the last section of chapter 19 that we'll discuss, and then we'll be done with chapter 19. What we're going to be talking about with this is complex ion formation. And what that is, a complex ion generally takes on the form of a metal with some kind of positive charge reacting with what we call a ligand, or sometimes you'll hear it pronounced ligand, either way. And the ligand can have any charge. It typically is either negative or neutral. And what we end up with is the formation of the metal ligand adduct. And so we're forming a bond between these two. And this is actually just our Lewis acid-base theory in disguise, where we typically have the ligand is a Lewis base. It has an excess of electrons. And the metal is our Lewis acid. It will accept electrons. So the metal is usually electron deficient, and the Lewis base, or the ligand, is electron rich, and it will donate electrons onto the metal and form the what we call a complex ion. And it can do this several times over to where we end up with multiple ligands around the metal. And they don't have to be the same ligand either, but for simplicity's sake we'll just keep them all the same, and you'll cover some more complex stuff later on. So this would be the Lewis adduct, or what we're going to call a complex ion. And the ion comes from the fact that if the ligand is neutral, then it just retains the positive charge from the metal, or if the ligand is negatively charged, it'll typically add on to it'll cancel out the positive charge of the metal. And if there's enough of the negatively charged ligand, then the complex ion will take the remainder of that charge. So we'll see an example here. If we look at hydrated metal ions, so if we have an ion like iron ion, Fe2+, it doesn't just float around in water. Water will react with it. In this case, we're going to take 6 water molecules because there are 6 coordinate directions or 6 orbitals that can react on the iron molecule. And we'll form the complex ion, what we call iron hexaquo. It's iron with 6 water molecules. And because water is neutral, this just retains the positive charge from the iron atom, or the iron ion. So this whole thing is FeHO2, H2O 6, 2+. So it just retains the 2+ charge from the water molecule. And again, what this kind of looks like from a molecular perspective is we have our iron atom, which is electron deficient. It wants electrons. And we have our water molecule, which is electron rich. It has some lone pairs. And it will donate electrons onto the iron atom and form a bond between those two. So again, the iron atom is a Lewis acid, and the water is a Lewis base. And what we end up with between those two is our Lewis adduct. And this can repeat 6 times over to where we have iron with 6 water molecules around it, and a Lewis structure would look something like this. Just an iron atom surrounded in a octagonal arrangement with 6 water molecules. Now we can form, so this is just a hydrated metal ion. So you put a metal ion in water, it's going to naturally do this. Some ions, or some other ligands, will compete for those waters and can actually replace the waters in a stepwise reaction, but the net reaction we'll just consider is that if we have an iron and 6 water molecules, so iron hexaquo, and in this case we're going to say the new ligand that's going to swap out for water is cyanide, which is also very electron rich. So let's just remember cyanide. The Lewis structure for cyanide is carbon with a triple bond to nitrogen, and they have 2 lone pairs on either the carbon and the nitrogen, or excuse me, on both of them. And it's actually the lone pair on the carbon atom that is going to be donated away. And so this repeats 6 times over to form iron hexacyanide, And because there are 6 negative charges from the 6 1 minus of the cyanide and only 2 plus, we end up with a 4 minus charge on this whole complex ion. And we also end up with the 6 water molecules that we kicked out. So this is called a complex ion formation. We're forming a complex ion of the iron hexacyanide from a hydrated metal ion. So technically the iron hex aquo is also a complex ion, but in this case we're just going to consider the formation of the iron hexacyanide. So if we were to write a formation equilibrium from this, Kf, it's the last K value we'll learn, I promise. If we learn Kf, or we write Kf for this, it would be the products over reactants, as we've always been doing. So it's the concentration of the iron hexacyanide and the concentration of water, and the water is to the 6th power, over the concentration of the iron hex aquo times cyanide to the 6th power. Now, because the concentration of water is essentially constant in these equations, this becomes 1, and we just forget about it. These Kfs, now we've been working with Kfs that have been very small, so Ksp is a very small number. Things are not very soluble in that case, or Ka or Kb are very small. We're dealing with weak acids and bases. Kfs, these molecules tend to want to undergo these processes. Kfs are typically anything greater than 10 to the 6th. So in this case, for this specific reaction, Kf is 10 to the 35th, or 3 times 10 to the 35th. Most Kfs are greater than 1 million, so 1 times 10 to the 6th. So if we combine this with a species that's not very soluble, we can actually use a complex ion formation to increase the solubility of something that's not very soluble. So for example, from one of our previous examples, we were dealing with iron sulfide, which is not very soluble, but we can dissociate it a little bit, and we form iron 2 plus and S2 minus. And the Ksp for these is 8 times 10 to the negative 16th. So again, not very soluble at all. But if we couple that, and we take that iron 2 plus and react it with cyanide, so essentially we'd have a beaker with the iron sulfide in it, and we would dissolve some cyanide into it. We get the formation of the complex ion. Let's make that a little more clear. Which we know has a Kf of 3 times 10 to the 35th. So the net reaction for all of this is that the iron ion, Fe2 plus, cancels out. The net reaction becomes iron sulfide plus 6 moles of cyanide, gives us the complex ion FeCN6, 4 minus, and the sulfide ion. So what we want to see here is what's the overall K value? How soluble will this be, or how far will this reaction go? Where does this equilibrium lie? Well, that Kf value, since we're just taking these two reactions and adding them together, what we do for that when we add reactions together, remember from earlier we learned about equilibrium. When we add two equilibrium together, we multiply their equilibrium expressions, or their equilibrium constants, to get the new equilibrium. So K overall is simply equal to Kf times Ksp. So K overall in this case is going to be 3 times 10 to the 35th times 8 times 10 to the negative 16th. So we end up with a overall equilibrium expression for this net reaction of mixing iron sulfide with cyanide to be around 2 times 10 to the 20th. So we would say that this equilibrium heavily favors the products. Essentially, it goes to completion, and we've made the iron sulfide over 10 to the 35th times more soluble. So using a formation reaction, which is very favorable. So again, we used a formation reaction, Kf, which is really high, to couple that with a thing that's not very soluble at all, times 10 to the negative 16th, for the KSP. We've coupled these two reactions in order to make this go to completion, and we essentially dissolve all of the iron sulfide. And that's what we need to know about complex ions from this type of equilibrium discussion.